When you think of any mechanical system, a gearbox in particular, gears are probably the first thing that come to mind. That's because they're one of the simplest and most efficient means of transmitting rotational power and torque, which makes them perfect for so many applications. And together with belts, chains, and wheels, they're probably the most common methods of transmitting rotational power. But what if I can't use any of these? Is a gearbox still possible? Is transferring rotational motion at all possible? Oh, and in case this wasn't hard enough, I'm saying no clutches either. So basically, all of the key parts I'd normally reach for when making a gearbox are completely off the table. Well, if we're just considering rotational transmission, then yes, there are other options, like this Schmidt linkage, or this configuration of lift arms. However, in these mechanisms, the input and output need to turn at the same speed so the levers stay aligned. This means that rotational speed, and therefore also torque, are always constant from the input to the output, so we can't create different gears using these. If we try to make the outputs turn at different speeds, it just won't work. So what other options do we have? Well, torque converters are pretty common in real-life applications, which use fluids to transmit power between rotating shafts. But I had my doubt about trying to build a watertight Lego structure full of moving parts, and more importantly, I really wanted to see if I could design something completely new. So, I had to think about the underlying principle that makes gears, belts, and the other common mechanisms work. They all rely on applying a force tangentially to a wheel at a certain distance from the pivot. Changing the distance to the pivot changes the output torque and the gear ratio. But how can we achieve this other than with these components? Well, this is what I came up with. We've got a rope on a drum, and a lever linked up to this axle. By turning the input, the output also turns. Well, at least for the first half turn. After that you can see we've got a problem, but I'll come back to that in a minute. This drum and string show the same principle as the other mechanisms. And if I vary the drum's size, it varies the output speed and torque. You can see that the output turns further despite the input turning the same amount every time. This design will actually have some benefits over gear-based gearboxes, but I'll get to that in a minute. We can hook the input up to a motor, but we see the problem I mentioned before. The lever can pull on the string, but not push it back. This will actually be a helpful feature later, but for the moment we need to deal with it. Obviously, the drum can't keep rotating in the same direction forever because it will run out of string, so we need something to rotate it back so it can be pulled forward again. My first thought was to have a rubber band to pull the drum back, kind of like in a rowing machine, but this had two big issues. Firstly, some energy is wasted every cycle by stretching the band. More importantly, power is only transmitted during half of the cycle, while the motor's power is completely wasted during the other half. A far better solution is to have two of these mechanisms, with the input cranks 180 degrees out of phase. These few gears make the output axles rotate in opposite directions. Now, each of the mechanisms takes care of one half of each cycle. The problem here is that the output axle rotates back and forth rather than steadily in one direction. This mechanism always turns the output in one direction, regardless of what direction the input turns. It's sort of like a mechanical equivalent of an electronic rectifier. Now, you might be thinking, this looks like a lot of gears for a gearless mechanism. For these gears, there's actually a clever fix. If I flip around this drum, I can just connect the axles directly to one another, so the strings naturally pull the drums in opposite directions. This removes the gears and also reduces complexity, a win-win if you ask me. As for the other gears, here are my excuses. Gearing down the motor doesn't count since it's not a part of the gearbox. As for the rectifier, I'm sure there's a way to make one without gears, but I wasn't smart enough to think of it, and I'm not sure it would be as efficient either. Speaking of efficiency, there's actually another change I'm going to make. Every time the output changes direction, a bit of motion is lost in the rectifier. To reduce this, we want the drums to turn as far as possible per cycle. I can do this by moving the attachment point of the strings from here to here. Now, the drums turn twice as far during each cycle. So now that we've got one of the 3 gears in place, let's add the other 2. So what I've got here is the most basic configuration, where the inputs for all 3 gears are connected directly to the input axle, and all 3 drums are connected directly to the output axle. Also bear in mind that in this model I've only got one of the 2 drums for each gear for simplicity, so I can explain how it all works, which means that I can only show it working for the first half turn of the input. So what happens when all 3 gears are directly connected like this? Well, you can see that when I turn the input axle, the string for 3rd gear stays taut while the other 2 go slack. This happens because the 3rd gear, having the smallest drum, turns the output the furthest. It essentially means that in this basic configuration, all the tension is going through the 3rd gear, and it's basically like the 1st and 2nd gear aren't even there. So now we know the setup we want for 3rd gear, but what can we do to make 2nd or 1st gear take the tension instead? Well, what if we make the 3rd gear string longer? Okay, well, now it's slack all the time, meaning 2nd gear takes up the slack, and the gearbox will run in 2nd gear. But we want the 3rd gear string to be taut some of the time, for when we want to run in 3rd gear. Imagine we put some kind of pulley in here. If we want to run in 3rd gear, we can pull it back so the string is taut. If we want 2nd gear, we can move it forward so the string goes slack. So, let's add it and give it a test. I've added on the pulley for 3rd gear. I've also added one for the 2nd gear string for the same reason. I understand that this is a bit hard to make out, but if both pulleys are held back, we're in 3rd gear. If I bring this one forward, we go down to 2nd. And if they're both down, we're in 1st. Now, let's add the other half of the gearbox to show it working fully. Oh, but before I do, I wanted to quickly explain why I've got these stacks of plates and towels between each of the drums. Well, initially, I was planning on using these drum elements. I even made custom ones for the other sizes of drums. The thing is, these work really well if the string is always taut. But if we go into 2nd gear and the string becomes slack, it will often get stuck on the outsides. Doing it this way, the strings never get stuck. So here is the same half of the mechanism I showed before, and this is the other half, which is just a mirror image of the same design to cover the other half of each rotation of the input. Now it's as simple as connecting the input axles together with a 180-degree offset, so the levers on one half pull the strings back, while the other half let them forward. The output axles for each half can be connected directly together, making sure these strings are taut so we don't have any excess slack between the drums. You know how I mentioned earlier that this design has some benefits over regular gearboxes? Well, as you can see, the drums for all three gears are connected directly on the same axle, meaning no gear shifter elements are needed, which is just as well since I said earlier that they weren't allowed. Now, I'm just linking up the linear actuators to control changing gears. And I can add a motor and give it a test. So, starting off, all the linear actuators are pulled back, meaning we're in third gear, which gives the highest speed and lowest torque. I know the motor's struggling a bit here, but we are in top gear. Now, I'll add on the same rectifier mechanism as before, so the output always turns the same way. Next, by extending the outer actuators, we switch to second gear. Here we've got a bit of a problem. We are in second gear, but the second gear strings have some slack in them, which means we're losing about half of the motion. This is happening even though the strings were all perfectly taut when we were in third gear. If I switch to first gear by extending the inner two actuators, this is now an even bigger issue, and we're losing all the motion. If we just permanently make the strings tighter, it will mess up third gear. But what if we connect the end of the string to this pulley? Imagine we connect the end of the string to here, with it running all the way around the outside like this, to where it's currently connected to the frame. When the actuator extends, it pulls the string tighter, giving us a different string tension depending on what gear we're in. For this to work, we need to connect the second gear string to the outer pulley, and the first gear string to the inner pulley. Since the input and output of the halves of the gearbox are connected, this will fix the problem just by doing it on one half. So, let's give it another test. We're starting in first gear this time because both sets of actuators are already extended, and it's working great, with the first gear string properly taut. Now, let's go up to second gear. The output is turning faster, and everything is still working smoothly. And finally, we'll go up to third gear. All's working perfectly. Before I end the video, I think it will be good to do a quick test. We can see that the output turns faster in higher gears, but more importantly, has it got more torque in lower gears? Let's find out. I added this drum to the end of the output and gave it some extra support. The plan is to hang increasingly heavy weights from this string and see how much it can lift in each gear. This meant I had to raise the whole gearbox up to give the weight some room to hang. And add a ratchet to stop the drum spinning backwards while the output changes direction. Now, I could just load up weight until the motor stalls, but I don't want to damage the motor or the mechanism, so instead I'm adding this clutch between the motor and the gearbox. The clutch will slip at the same torque regardless of what gear we're in, so if the output can handle more weight in lower gears, it means the gearbox is successfully increasing torque. Starting in third gear, let's see how much weight it can lift. We'll start off with just the weight of the holder, which is about 10 grams. That's working well. Now let's add on this 5 gram weight to take it up to 15 grams. The clutch is slipping a bit now, but it's still just about managed to lift it. Now I'll take it up another 5 grams to 20. It was just able to move it a little, but the clutch was slipping a lot here, so I'm going to call this the limit. Based on the radius of the drum, this gives us a torque of 0.31 Newton centimeters. That's kind of low, but bear in mind that the output's turning pretty fast. Going down to second gear, let's see how it does. With 40 grams, it's still going strong. It looks like 50 grams is the limit here in second gear. As for first gear, I'm going to start with 50 grams since I know first gear is going to be stronger than second. It's not the fastest, but it is lifting it and the clutch isn't slipping. I'm so confident in how strong it is that I'm jumping straight to 70 grams. The clutch is finally slipping slightly, so I'm going up to 75. And finally, that's the max. Putting this in the table, we get an output torque of 1.18 Newton centimeters. Using this number and the radii of the different drums in the gearbox, we'd expect to get torques of 0.89 and 0.59 Newton centimeters for second and first gears. The actual values aren't that far off, but it's clear that there's a decent amount of extra loss in second and especially first gear to bring the output torques down below what we'd expect. Nevertheless, it's clear that we're getting plenty more torque in the lower gears. And that brings me to the end of the video. I'm really glad this worked in the end because there was a lot of strings to thread around. Of course it's not as compact or efficient as a regular gearbox, but that wasn't exactly the point. I'm planning to use this gearbox again in an upcoming video, but until then, thanks for watching.